Hi, everybody. This is the week 2 chat over section 2.4, which is continuity and one sided limits. So that's what we'll be discussing in this section, continuity and one sided limits. So let's just take a look at three functions that are not continuous. And these are three different functions. None of these three are continuous, but they're not continuous for three different reasons. So let's take a look at all three of these. The first, if you look at the function, this one right here, between A and B, the function goes, but all of a sudden there's a little hole there. In other words, between two points in a function, between two x values, in order to be continuous, every x value has to be defined. There has to be an answer for every x value. So if you look at this at x value c, the function f of c is not defined. We don't know what it equals because at this spot there's a hole. So this function is not continuous. Here's another function that's not continuous. This time at fc, we are defined. We do have an answer, whatever that answer is, but we do have an answer. So at every function, at every x value in this function, if you look, we have a y value. We have an answer. Right after that, here. So in that interval, we do have a y value for everything there. However, this function is not continuous because the limit does not exist. Do you see, as you're approaching an x value of c from the left, this function is the answer y is approaching this number. As you approach c from the right, it's approaching a different number. Do you see they're approaching two different numbers? So we say this function is not continuous because the limit does not exist. Remember, for the limit to exist, at the c value, at whatever value we're talking about, the as the x values approach that c, the limits have to be approaching the same number. And here they are approaching this number way down there, and this one's approaching this number, two different numbers. So that function is not continuous because of that. Here, once again, every x value is defined. Even at f of c, it's defined, and then we continue on. So every x value is defined. And the limit does exist because when I approach here and I approach here, it's approaching the same y value. So it passes this test. It passes, it passes the every y value exists. It passes, yes, the limit exists. However, there's one more stipulation that for this to be continuous, the f of c has to be the same as the limit. So do you see how when we say what's the limit of this function, let's say this value right here is 7 for a y value. So the limit of this equals 7. The limit as x approaches c is 7 because from the left and the right, it's approaching 7. However, the actual function for c is 6. Do you see? If you say, what does f of c equal? Well, f of c equals this number right here, and that might be 6. So the limit and the actual function, the y value of the function at c, don't equal each other. So we say this function is not continuous. So these are the three rules of why a function is not continuous. So we needed to know that. So that was on my first slide, and I took that right out of the calculus book. Okay, so also we need to understand removable and non-removable discontinuities. A removable discontinuity is a hole in the graph, and this is often caused by when you have a factor and in the numerator and denominator that cancels each other out. It's often called by that. A non-removable really can't be factored if you look at the denominator of a rational function. It says it does not have a limit at the discontinuity. In other words, a non-removable hole has an asymptote. It has a hole there, but it's an asymptote. So it's not really a removable hole. It's an asymptote that we have. It's a line that your graph cannot cross. So let's take a look at a couple of them. If you look at this function here, it has an asymptote that goes right through it. So this is a non-removable discontinuity. In this function, if you can see it, that's actually a hole. If we have a hole, then it's a removable discontinuity. And once again, if it has an asymptote, it's non-removable. So that's kind of good to know, good to remember. In the book, this came up. Normally, I wouldn't even talk about this, but since we have a homework problem, I wanted to show you this symbol in math. And that's called the greatest integer function. So the greatest integer function in this case is when you look at this decimal number, the greatest integer, if you look at 2.5, the next integer would be 3. And I'm not sure what happened here. Like here, the next integer would be 4. So this greatest integer function just lets you know what's the next greatest integer. So in the book, there's an example of the function of the greatest integer function. So if I just do some x values to show you this, and we'll look at the y values. If an x value is 0.1, if an x value is 0.1, in this function. We keep it at 0. Do you see? We're going to keep it at 0, the greatest integer function. So if you look at it, the greatest integer that happened before 0.1 was 0. If I do 0.9, the greatest integer before 0.9 was 0. Do you see? When x value is 0.9, my y value is still 0. Once my x value goes to 1.1, goes higher than 1, then my y value, 1.1, x is right here. Do you see? Now my y value is 1. If I go to 1.7, the greatest integer of 1.7 is 1. We don't get, even 1.9 is 1. We don't get to the next higher integer until we pass that threshold of 2.0. Then 2.1 is 2. 2.7 once again is 2. Eventually we'll get to 3.0. Once we get to 3.0, then we'll go up to 3. And if you see, it's filled in at 3, and then it'll keep on going. So I just wanted to introduce that greatest integer function. I might have said it wrong when I was back here. Let me go back one slide. So I did say it wrong. Just realized it. The greatest integer function, if you look at the greatest integer of 2.5 is 2. The greatest integer of 3.5 is 3. So I did say it wrong in the previous slide. Once you pass the threshold of the next whole number, the next integer, then that integer will be the greatest integer. So I wanted to introduce that greatest integer function just because it's in the homework. All right, so we're still looking at discontinuity. And for this problem in the book, it just says discuss the continuity of this function, and we even have it graphed. And if you look at this graph, the graph only exists between -1 and 1 inclusively. So if you discuss the continuity, if you look at the graph, there are no holes or asymptotes or anything. So the graph is continuous between -1 and 1, including 1 and -1, because those are filled in at that spot. So this is continuous as you're moving from left to right, and it's continuous as I move from right to left. So let's discuss the continuity of this function. So I'm going to graph tangent x on my calculator just to show you this really quick. So I go to y equals, if I go to y equals, I type in tangent x. My window's set for -10, 10, and 10, 10. Now if I hit graph, you can actually see the tangent function. There's my window. So I'm going to try to draw that on my paper here. Good luck to me. So a tangent function looks like this. If I could, like I said, it's hard to draw this. I'm going to draw it with a different color. It goes like this. I'm going to try to draw it. That's a really bad, but it looks more like this, and then it turned down, coming over. If you look at this function on a calculator, I really drew it bad. I'm going to try to get better. Let's try this one, coming down. Try this one, coming down. Okay, so in a tangent function, we have these asymptotes. And if you look at your calculator, the asymptote looks like it's at about 1.5 or something. Do you know, once again, tangent function is sine x over cosine x. So we have asymptotes where our function becomes undefined when cosine x equals 0. So at what cosine does it equal 0? And that would be pi over 2. If you go to your unit circle, you look at the cosine. I think I have the unit circle with me. I thought I had it. Oh, I have one right here. So this is a copy of the unit circle that I gave you guys in your notes that you're allowed to use for the test. Once again, there we go. Do you see the cosine is the x value of the circle? Where is the cosine 0? At pi over 2. Also, at negative pi over 2, if you look at the domain for the tangent of x on our formula sheet, so anyway, if you look at your trig sheet, formula sheet that I gave you, it shows the domain of a tangent function is from negative pi over 2 to pi over 2. This makes it continuous. Do you see? That makes a tangent function continuous if you stay within the boundaries of negative pi over 2 and pi over 2. So the question, I think, is, when is a tangent function continuous? If you stay within the boundaries of negative pi over 2 and pi over 2, and then you multiply that by pi, because you can do it again when you come over here. If you multiply this by add pi to that, not multiply it by pi, add pi to that, then you can do it between pi. This next one would be between pi and 3 pi over 2. The next one would be between 3 pi over 2 and 5 pi over 2, and so on and so on. So that's how a tangent function can be continuous with no holes. All right, I am going to go to the next slide. I get a little messy here. Let's look at this function. We've looked at this function before on our calculator, I believe. I'm going to put it in my calculator and show you the sine of 1 over x. So it's a weird graph, and you have to change Hey, what happened to my video? Oh, there it goes. It's a weird graph, and you have to change your settings on your calculator. There's my graph, sine of 1 over x. There's my window right now, and if I hit graph, there's my graph. I'm going to try to change my window so I see what's happening better. If I change my x values from -3 to 3 and my y values, I'm going to leave them alone for now and hit graph and see what happens. You can see a little bit better what's happening. I can even change my y values a little bit to make it more clear. -3 to 3. Let's see what happens. There we go. Let me get closer in on my x values. I'm going to go from -1 to 1. If you look at this function, it keeps it oscillates back and forth. I can even get closer if I do my window from -0.1 to 1. Let's see what x scale. I don't think it matters on what x scale should be. Oh, let me. I said it wrong. Let me say the x values from 0.1 to, sorry, -0.1 to 0.1. There we go. Now we should get a better view. Do you see how it oscillates back and forth? But what's happening at 0? There's an error at 0. And the reason why, once again, there's an error at 0, if you look at a function, you can't put 0 in the bottom of that fraction. So there is definitely a discontinuity at 0. So where is this function continuous? This function is continuous everywhere except 0. So, I mean, that's what they just wanted you to talk about. So that function is continuous everywhere except 0. It's really hard to visualize that unless you went to your table and saw the values, the x values that I just looked at. Okay, so the intermediate value theorem is next, slide 11. And by the way, make sure you understand this or take note of this, because I believe this is on test 1 and many people mess this up. The next question, the next slide is what people mess up. But understand what the intermediate value theorem is. It says is if a function is continuous and it's closed, you're staying between two a left boundary and a right boundary, then there exists a number between the boundaries. It just says if we have two numbers here, if we know this number and we know this number, and if this is continuous, then there are numbers in here. Intermediate value theorem, there are numbers in there. And this comes useful because it'll tell us what kind of numbers are in there. In other words, if I was here's a real life example of that. If I was 5 foot tall when I was 12 years old, and then I was 16, when I was 16 years old, I was 6 foot tall. Right here, I was 5 foot tall. Here, I was 6 foot tall. At some point, I was 5'6". I didn't just go from 5'5" to 5'7". I didn't jump. I could have been, 5'5", 5'5.1", 5'5.2", and so on. You're growing continuously. All the numbers are covered in that basis, right? All the numbers are covered. If this is continuous, all the numbers are covered. So in this problem here, it says we have this function. This should be the lowercase f. We have this function, x3 plus 2x minus 1. It says use the intermediate value theorem to prove the function has a 0. A 0 means that if we put an x value in there, y will equal 0. That's a 0. A 0, is a y value that equals 0 when it says we have a 0 between 0 and 1. So the way to look at this, you can look at a graph at first, but I want to show you how to prove this. Let's look at this graph. Put this graph in your calculator. I'm going to put it in my calculator, and then I'm going to show you how I want you to manually, on paper, show this. X to the third plus 2x minus 1, and I'm going to graph it. And let me change my window to -2 and 2, -10 and 10. My window should be X and Y's. Let me change that. Give me a second before I show you. Let me fix it. I think we're okay. So I look at my function, x to the third plus 2x minus 1, and I graph it. I set my window where the x's are -2 to 2 and the y values are -10 to 10. So when I graph it, it's the example said, don't forget the domain of this example says between 0 and 1. Do you see the domain said between 0 and 1. Here's 0 on my graph, and here's 1 on my graph. So between 0 and 1, this function is right here. Between 0 and 1, that's the function. So the question asks, show that there's a 0 between 0 and 1. And if you look, the 0 is right there where y crosses, where y is 0. When we look on the graph, y0 is right there. So the 0 is about right there. So there is a 0. We can see it on the graph. So how do you show this on a test? Well, what you do, one way of doing this, and this is the way we do it for our test in this particular point, first plug in 0 into the function. 0 to the third plus 2 times 0 minus 1. When you do the math, you get a -1. So when you plug 0 in the function, you get -1. When you plug 1 in the function next, we're going to plug 0 in, then we're going to plug 1 in. If I plug 1 into the function 1 to the third plus 2 times 1 minus 1, I get 1 to the third is 1 plus 2. 1 plus 2 is 3 minus 1 is 2. Do you see my y values go from -1 to 2? Remember, this function is continuous for the between x0 and 1. The function is continuous. So if we went from -1 to 2, at some point -1 if you look at a number line of -1 to 2, to get to 2, from -1 to get to 2, you had to bypass a 0, right? You're at -1, -0.9, -0.8, -0.1. At some point, you have to bypass 0 to get through it. So if you have one function, if you have one lower limit is a negative, the other lower limit is a positive, at some point between those two numbers, you had to bypass 0 as far as we're talking about the y values. And so it says use the intermediate theorem to prove that there is a 0. If you have a y value of -1 and a y value of 2, we know this function is continuous. There had to be a 0. just because this is continuous, and in order for you to start at -1 and get to 2, you have to bypass 0. So that's what we wanted to do for that. That's the intermediate value theorem. And the same thing we talked about in the real life. If you're at 5 foot and next time you measure yourself at 6 foot, at some point you were 5'6", 5'7". At some point you were somewhere in between there on the number line, and that is 5.4. Or not 5.4. 2.4 limits and their properties and continuity. Oop. So I hope that helped as far as covering that section. So the homework shouldn't be too bad if you watch this video. Let me know if the videos are helping any, or let me know if you're even watching the videos. You guys have a good week.